So hi everyone, welcome to this last NITheCS Mini-school series of November. So this is the mini-school on from electrons to qubits, exploring the frontiers of electronic structure. Unfortunately, Professor Francesco Priticcioni, who's the director of NITheCS, couldn't be here to introduce our speaker Shane McFarthing today. So in his stead, I'll be introducing our speaker. So I'm Dr. Graham Pleasance. I'm a postdoc in the quantum research group here at Stellenbosch University. And I believe today's lecture will be on more focused on the quantum algorithms. So I think the title of the lecture is State-of-the-Art Quantum Algorithms for Finding Ground States. So before I hand over to Shane, let me just remind you, if you have any questions for Shane, then just please feel free to post these in the Q&A, and these will be addressed at the end of the lecture, or you can be given the opportunity to ask your question in person. So yeah, without any further delay, let me hand over to Shane.
Great. Thanks very much, Graham, for the introduction. Yeah, so today is the last lecture in the mini-school. And as Graham said, it's going to be focusing on the quantum side more, so focusing on the quantum algorithms. So just to do a recap of what we covered last week. So we took our first look at conventional quantum computing algorithm that's used for solving electronic structure problems. And that algorithm was the Variational Quantum Eigensolver. So what we did was we introduced the algorithm, talking about how it's a hybrid quantum classical algorithm for finding the ground state of some chemical systems. So the VQE is used as a method to find these ground states, and it combines both quantum and classical computing resources. And kind of the overview of how that method works is that we try to prepare those ground states in an iterative manner. So we use a quantum circuit to prepare a state on the quantum device. And that state represents the wave function of the system that we're looking for. And what we try to do is iteratively improve that wave function that we've prepared. And the way that we do that is by using a classical optimizer to improve the circuit's ability to prepare that wave function. So the quantum circuit is parameterized. It contains classical parameters that dictate certain rotation angles on the quantum computer. And in order to know how to update those parameters to improve the state that the VQE has prepared, it needs to have some sort of metric to do that. And the metric that is used is the energy of the state. So we evaluate the expectation value of the Hamiltonian with respect to the state that's being prepared. And that gives us an energy of the state. So when we're looking for the ground state of a chemical system, we're looking for the electron configuration that provides the lowest energy. And it's important for some chemical property studies. And what we try to do with VQE is to iteratively change the state that's on the circuit so that the energy is lowered. The components that we use to do that are the quantum circuit that prepares the state itself on a quantum device. And then we have the Hamiltonian, which is really crucial for evaluating the energy of the state, since the Hamiltonian represents the operator of the total energy of the system. So if we have a chemical system, a quantum circuit can be system agnostic. You can have the same circuit for different chemical systems, and using the quantum device, which doesn't depend on the system, the way that we tie the application into the specific chemical system that we're studying is by using the chemical Hamiltonian. So we have the Hamiltonian, the circuits, we perform the training using the optimizer, and these all work together to try to produce that state with the lowest energy, which forms a solution to the Schrödinger equation. And we discussed how VQE, even though it's a promising algorithm that was it was first introduced many years ago, like 2017, 2016. At the time, there was a lot of hope for it working, but unfortunately, with the current state of the quantum devices that we have at the moment, it didn't really have the performance that we hoped for. So there were some issues with regards to being able to effectively train the quantum ansatz on the quantum computer. So we weren't really able to lower the energy of the state. And also the quantum circuits that we were using to generate the wave function were too deep. So there were too many gates in those circuits. And this kind of hampered the performance of VQE to the point where it's not really an algorithm that someone will use today on a quantum device to try to solve the electronic structure problem. But there have been advancements that address these two problems, and today's lecture is going to cover those. So the lecture is going to be on state-of-the-art algorithms that the methods that people use to try to solve electronic structure problem today on quantum computers. So it's going to cover the recap more in detail of the issues that VQE has that I've just spoken about. And then we're going to go through some methods that people use to address those issues. So the first one is going to be about ansatz construction to try to address the issue of having quantum circuits that are too deep. And the second one is going to be taking a look at ways to improve the trainability of these circuits on a quantum device. So we're going to be taking a look at an algorithm called quantum SCI, which ties into the classical SCI that we spoke about in lecture 2, but we'll do a recap of SCI as well. And then just to close off, we kind of summarize the mini school and what the takeaway is, tying everything together. So just to get straight into the first issue that I spoke about, when we look at the VQE algorithm, the reason it should work is because we're supposed to be able to systematically lower the energy of the state that we've prepared. And the training, the classical training of the circuit parameters is the avenue that we use to do that. So we have our quantum circuits, and we need to update the parameters to produce a state that minimizes the energy. And that minimization problem can be visualized as this equation here. So we try to pick the classical parameters theta that will produce the lowest energy expectation value, which is this expectation value here of the Hamiltonian with respect to the state psi theta. And that state psi theta is the state that's prepared on the quantum device by applying the parameterized quantum circuits to our initial state. So what we're trying to do is find these thetas that will give us the state with the lowest energy. We keep the circuit structure the same, and it's only the rotation angles that we change. And VQE works if this optimization can work. So if you're able to lower the energy, then we know that because the algorithm is variational, we can just continue to try to minimize the energy, and the answer, the energy that's provided by VQE is lower bounded by the energy of the actual system because of the fact that it's variational. However, so if we look at the quantum devices that we have available today, we refer to them as NITheCS devices. So they're noisy because we don't have error correction on them. So there's a lot of interference happening. There's a degradation of the information stored on the device. They're intermediate scale, meaning that we don't have a lot of qubits. So that's the reason why we don't have error correction as well. So error correction is basically a way to build redundancy into the device so that we can try to avoid loss of information due to the noise from the environment. And you need millions of qubits in order to implement that error correction. But currently on the devices that we have, for a superconducting qubit device, we have maybe up to 150 qubits. And there's some other technologies that have maybe up to 1,000 at most, which I think some neutral atom quantum computers are coming out. They'll have that. But in general, it's still like a long way off the millions of qubits that you would need. So we call it intermediate scale because it's not the full scale, but it is what we have at the moment. And these devices are kind of characterized entirely by the amount of noise that they have. So we have noise in the device from in the gates. So we have errors in the gates. We have errors when you read out the measurements from the quantum device. We have low coherence times. So the amount of time that you can hold the state you prepared on the quantum device is really limited. And all of these things compound to affect the evaluation of this energy in VQE. So when you perform VQE, this energy estimation is crucial for being able to give the classical optimizer the information that it needs to prepare parameters that will actually improve the energy. And we compute this by performing a lot of measurements on the quantum device using the Hamiltonian, and it has some outcomes. And if you have noise on the device, then the quality of those measurement outcomes is seriously degraded. And if we are degrading the outcomes of the measurements, then we're degrading the accuracy of the energy, which means we don't truly know what the metric of that state that we have on the device is. The result of that is if we try to visualize the cost landscape that we're searching around, we're looking for the lowest points on that landscape, because that's the quantum state that corresponds to the lowest energy. The optimizer needs information to know which way to go on that cost landscape in order to be able to find the global minimum. But if we are degrading the information that the optimizer is getting, we can end up with the situation where our cost landscape is flat. So if we use the gradient of a state to try to improve the quantum state on the quantum device, that gradient can actually vanish exponentially with the number of qubits. And what you get is just this flat plane, which we refer to as a barren plateau. And what we end up being unable to train our states. So rather than have a guided walk through the cost landscape that heads towards the local minimum using something like gradient descent, you'll instead just end up with a random walk where we don't know which direction to go and we don't know how to update the parameters of the circuits to try to improve the quantum state. The other issue that I mentioned is the circuit depth. So when we try to use the quantum circuit to generate the wave function, it needs to be expressive enough to be able to reproduce wave functions of complex chemical systems. But the counter effect of that is that in order to model that complexity, very often the circuits are quite deep. And so earlier I mentioned on the NISC devices, we have the gate errors. If you have a lot of gates in your quantum circuits, and each gate has a certain error rate, then you end up with this compounding error throughout your circuits. And the deeper your circuit is, the worse that error gets. So you might end up at a point where you've applied a circuit that's so deep. At the end, theoretically, you should get a state that corresponds to what you're trying to do. What you really get is just random noise, because the gate errors compounded upon each other and did some random things like randomly flipping the states of the qubits, perhaps applying different operations, and you end up in a state where we don't have the target out at the end. Instead, we just have some random result. So what we have to try to do is reduce the depth of the circuits to minimize the opportunity for that compounding of gate error. And the flip side of that is, because it's a balancing act, is that when you reduce the circuit depth and you make the circuit more compact, you lose some of the expressivity. So if we lose that expressivity, sometimes we can't model the wave function for certain chemical systems. So it's really important to try to satisfy both of these. We have to try to make circuits that are shallow enough that they can run on the device without a lot of errors and noise. And that circuit still needs to be expressive enough to be able to model the wave function that we're looking for. So we're going to take a look at some solutions to these problems, and we're going to start off with the circuit depth. So the approach that we're going to take is trying to dynamically build the quantum circuits. So rather than just having a circuit structure, we're going to try to iteratively build that structure so that we can keep the circuit shallow. So just to start off with, last week when we discussed VQE, we spoke about the unitary couple cluster ansatz, which also builds on the couple cluster theory from the second lecture. And essentially what it is an exponential ansatz where the operator T is a cluster operator that is defined in terms of excitations of electrons. So by excitations, we're moving electrons around from orbital to orbital, and it allows us to capture some correlation in our wave function, which is really important for being able to get chemically accurate results. And this ansatz is simply formed as the sum of excitations of different degrees. So we have the T1 operator, which is all single excitations. So we move a single electron from one orbital to another. We have the T2, which is the doubles, so moving pairs of electrons around, and then it goes all the way up to moving all of the electrons at once. So if we have n electrons, then you go up to n degree excitations. And that gives us this exponential ansatz. And what we've seen is that because of the form of the exponential ansatz, it's really good at systematically capturing that correlation. Since we are, if you expand the ansatz as a Taylor series, you find that you get interaction between the excitations that can prepare excitations of a higher degree. So it's a really good ansatz for trying to capture the correlation in the system. If we take a look at the circuits that we use to implement this, if we have our exponential ansatz is the e to the power of the sum of some fermionic operators that define the excitation. after we perform a mapping so that we can bring those operators into the spin space, which we use for the quantum computing or quantum device, we have this sum of exponentials. And you could break down each exponential operator and prepare a quantum circuit for it using a trauterization process. And this is just an example of the circuit block for one single Pauli operator that's been implemented as an exponential ansatz. And as you can see, we have these basis rotations that occur first that correspond to exactly what the Pauli word is. We have to undo the basis changes at the end, and then in order to change the occupancy and the phase, or to satisfy the anti-symmetry of the wave function, we have these C0 gates as a ladder, and we have the Z rotation. Now, the problem is that even though we're moving, in this case, you might be moving 2 electrons around. As you increase the number of qubits, if you had to try to interact or entangle 2 qubits, one at the top of the register on the quantum device and one at the bottom, you're going to end up with this ladder of C0 gates going down the whole quantum register. The result of that is when we prepare the circuits for every single excitation in the UCC ansatz, we end up with thousands and thousands of C0 gates. And these 2 qubit gates have a high error rate on quantum devices. Well, it's always improving, but there's an error rate that's associated with using these gates. And if you have that many of those gates in your circuits, you're going to run into issues with regards to the fidelity of your state and how accurate it is compared to what you're trying to do. So we end up with too many C0 gates. And also, when we consider the wave function that we're trying to prepare, the number of excitations scales exponentially with the number of electrons in the system. So that thousands of C0 gates that we need, that's only for some small to moderately sized chemical systems. If we try to deal with systems that were really relevant for industrial applications or some really challenging problems, for example, if you try to look at nitrogen fixation, there's a really complicated compound that you have to model for that. You would have no chance of preparing a couple cluster ansatz for a system that big. You would end up with probably hundreds of thousands to millions of C0 gates. So what we need to be able to do is try to reduce the number of operators that we have to implement in the circuit. We took a look at the UCCSD ansatz, which is where we only use the singles and double excitations. But that circuit is still too deep, and it has some problems with obtaining the accuracy that we need because it misses some correlation. But it did introduce the concept of truncating the space. So we know that we can shorten these circuits by leaving out some of the excitations. But what we really need to do is figure out how can we select the operators that will shorten the circuit but not have the accuracy issues. It will still allow us to model the wave function that we need. And an algorithm that does this is the adapt VQE algorithm. So it's the adiabatic derivative assembled pseudo-trotter algorithm. And what it essentially does is it starts off with a small circuit and it iteratively builds up the quantum circuit by monitoring the performance of that circuit itself. So if we take a look at the overview of the algorithm, we'll start off with some initial circuit, which is typically just a Hartree-Fock state. And what we do is in a loop, we build up the circuit until at the end, once the algorithm has converged, we output an optimized ansatz. And it's an ansatz that also meets our depth constraints. So we're trying to do that balancing act of making a compact circuit that also is really expressive and is able to provide an accurate solution. So if we go through the steps, so the first step will be to create a pool of the excitation operators, and we're trying to have some group of circuit operators that we can select from to add to the quantum circuit to make it bigger and more powerful. And what we do is we evaluate the gradient of each of those circuit operators to see which of those we should select to add to the circuit, which we do in step 3, where we add that operator and that new parameter to the circuit, and then we perform the VQE algorithm to optimize the circuit parameters. So it's an iterative process where it applies VQE in iterations. We build an ansatz, do VQE, and train the parameters of that ansatz, and then add another operator to that ansatz, and we continue the process until there's a convergence, and we output the ansatz that's been optimized. So to take a look at the steps in detail, the first thing that's really important is the operator pool. So these are like excitation operators that form the foundational elements from which we're going to build the quantum circuit. So for example, if this is one element in the pool, it's defined in terms of excitation operators. So this is just an excitation involving orbitals p and q of spin alpha, so the one spin top, and then we do a spin complement where we include the excitation for the other spin. So this is a single excitation from alpha orbital to another alpha orbital, and this is the same thing with beta orbitals. And then these are double excitations of kind of the same case. So if you were to select one operator of this type, you would be choosing to add these sets of excitations between the orbitals that you specify. And what we're trying to do is iteratively select operators from this pool to add to our circuit. And when we do the selection, we can do it with replacement. So if you use an operator in like a certain iteration, you add it to the circuit. The next iteration, you could add that operator again if that's what made the most sense. And by kind of doing this iterative building of the ansatz, we can make a compact but powerful ansatz. We're keeping the accuracy of the ansatz in mind at all times when we're doing this process, which is why we know that it should be expressive. And because we have control over how many operators we add to the circuit, we know that we can stop when it's getting too long. So the crucial aspect of the adapt VQE is really the operator selection and picking which operators to add to your circuit. So what we do is in each iteration, we pick either the single operator or the set of operators that will have the biggest effect on the energy that the quantum circuit can prepare from the state that the quantum circuit prepares. That'll have the lowest energy that we can possibly get. So we're just trying to improve it each time, and we just pick the operators that offer the biggest improvements. And when we do this and we're doing this selection, it gives us control. We have control over how many operators ultimately go in the circuits. We have control over which ones are being picked, and we can have some bias by maybe picking operators that will introduce the least number of gates and things like that. So if we take a look at, we've spoken about like wanting to do the selection, why we want to do it, what we're selecting from, but we need to look at how we perform the selection. And what we typically do is we'll use a gradient. So if you look at the pool of operators and we have every single operator there, we look at what would the effect be if we added that operator to the circuit? Would that effect be on the energy? What would that effect be on the overlap of the state that we prepare with some other target states? And this is how those expressions look. So in the first case, which is just the original one from adapt VQE, you use the energy. And if you're trying to check the gradient of the energy, what you'll do is you'll measure this commutator expectation value, and this psi m-1 is the state that you prepared, the quantum state you prepared in iteration m-1, and this operator is the quantum circuit prepared by the application of the operator that you're considering. So we'll consider each operator in turn, generate this operator, and measure this with respect to the state that we prepared in the previous iteration. And what this gives us is the gradient of the energy with respect to the addition of that operator in the circuit. So if you were trying to pick an operator based on this gradient, you would be saying which operator will have the biggest effect on lowering the energy when I add it to the circuit. And another thing that you can use is you can use the overlap. So adapt VQE as an algorithm was introduced a few years ago, and there've been a lot of different additions to it. And one that was found to have a really big effect on trying to produce as compact an ansatz as possible that has as few parameters in it as possible was to use the overlap instead of the energy. So what you do is you pick some reference wave function, so the psi ref. It can be it doesn't have to be the true state because we don't have that for a system that's large enough. It'll be some sort of approximation of that. So you could get this using selected configuration interaction or some other method. And what we do each iteration is we try to maximize the overlap between the state that we prepared on the quantum device with our ansatz and that wave function that we're using as the reference. And what we do is when we make the operator selection, we pick the operator that has the biggest effect on the overlap because we're trying to maximize the overlap so we actually get out a good state. We just pick the operator that will have the biggest effect and the biggest improvement on the overlap of our quantum state with the target wave function. So now we've done the selection. You are in a specific iteration. We've identified an operator that we want to add to the circuit. We add it to the circuit, and when we add that operator, it introduces a new parameter into the circuit. And in order to kind of proceed to the next iteration where we're going to make another selection, we need to optimize all the parameters and ansatz. So each iteration of adapt VQE, we apply just the full VQE algorithm itself using the ansatz that we generate at that point. So given an ansatz, we'll run the VQE algorithm on the quantum device, which trains the parameters in that circuit to try to minimize the energy. But unlike VQE, we're not actually reliant on the training at this point. We're just focusing, like the training for the final energy, we're just focusing on trying to produce as good of an ansatz as we can. And then we go into the next iteration and we make the selection of the operators then. So the reason we do this re-optimization is because when we're trying to consider which operator we should add to the circuit, we're trying to kind of not have any effects, not need to consider any effects from if we change the parameters in the circuit. We just know these are the best parameters that we have at this point for the circuit that we have. And now we can look at adding in more operators. So we kind of repeat those steps in an iterative process where we train the circuits, add an operator to the circuit so the circuit gets bigger, train the circuit again, and we continue to do this. And we have to stop at some point. And there's a couple of different options that we have to pick what the termination would be. The first one, which is really natural in the context that we're talking about, is to terminate once we've reached some limit on the number of operators. So the operators are linked to the depth of the circuits because they have to be implemented as quantum circuits. And when we're looking at the issue of having circuits that are too deep, we'll set some limits and say a circuit of this depth is acceptable, and let's do adapt VQE until our quantum circuit is that deep. Once it hits that limit, then we'll terminate and we'll just use that circuit for whatever we were going to do with it next. Another option is that instead of focusing on the depth of the ansatz itself, we can focus on the performance of the ansatz. So we'll look at either the overlap with the reference wave function, or we'll look at the energy that state is able to prepare, the energy of the state that the quantum circuit prepares. And we'll just simply continue to add operators until we get a convergence with respect to those metrics. The motivation for that is we worry about the depth of the circuit in as much as it affects the wave function and the energy that we get out at the end. If we have one that's too deep, we get out a bad state and a bad energy. But if we focus rather on how the quantum circuit is the quality of the solution that it's outputting, then we can just continue the process of applying adapt VQE until we just reach a convergence in that aspect with respect to the energy or the overlap. And then another thing that we can do is we can focus on the selection of the operators. So in each iteration, we have to perform a selection of an operator from the pool of operators that we have, and we use a gradient in order to know which operator we should select. But we can have a situation where there's not really any difference between the gradients for the different operators. We don't know if adding this operator will give us a better energy than adding a different operator. And once we have that the gradients, the norm of the gradients in our operator pool are below a certain threshold, at that point we can just terminate and we say, at this point, I don't know what would be the best operator to add, and I'm just going to call it here, and we'll just use the quantum circuit that we have at the moment. So those methods are used to kind of determine when we should stop adapt VQE. So we know that adapt VQE can make a compact ansatz that is still expressive, and the motivation for it is it's not really specific to adapt VQE. If you're looking at dynamically constructing a quantum circuit to take into account your needs, you can use different methods to do this, not just adapt VQE. And it's a really crucial consideration when you're doing quantum computing on a NISC device, is that you need to have components of your algorithm that are suitable for your needs, not necessarily for a general need that was theoretical, saying that this will give you the best answer when we have the best quantum computer possible. We just need to have the components that suit us. And this dynamic construction is really, really powerful in that sense, because it can give us a compact enough ansatz for whatever we specify compact to be. And it's still powerful because it's still expressive enough to give us a good accuracy. And other methods that can be used are, like, for example, you can use AI to generate these ansatz or these quantum circuits. So you can use a machine learning model to train on some information on the chemical system that you have. It can be unsupervised training, so you don't have to like have labeled data. And it can then generate an ansatz that satisfies the constraints that you give it. And this has been done in some papers, and they found that actually they were able to generate quite compact ansatz compared to the typical ones that we had spoken about before, like UCCSD and some other versions that had truncations. So there's really a lot of advanced methods that you can use for the dynamic construction of the ansatz, and it's still a growing field. Yeah, so that kind of concludes the circuit discussion for now, and we're going to go into the first problem that we mentioned, which was the trainability of VQE. So where the noise was stopping us from being able to train the circuits. So what we're going to take a look at is, rather than using the quantum device to give accurate energy estimations, which is where we're having problems, we're going to use the quantum device to kind of do a different functionality in an algorithm. So we're going to get into that in this section. So just to give a recap on a classical algorithm called selected configuration interaction. If you remember, the full configuration interaction is the exact solution to the electronic structure problem. We have an exponential sized wave function that includes every possible electron configuration, and we use an eigensolver, a classical eigensolver, to exactly solve for the amplitude, these CI amplitudes in the wave function. But when we're looking at ground states, we know that, well, it actually was discovered that the ground states of chemical systems actually depend on a much smaller number of configurations than that full exponential number. So there were methods developed to select those important configurations, and that is kind of the crux of selected configuration interaction, is trying to select the configurations that have the biggest effect on the energy while allowing us to still perform the diagonalization, because there's not an exponential increase in the quantum resource in the computing resources. So SCI is a way of reducing the full configuration computational overhead. And when we talk about the Hamiltonian that we're considering, if you represent it as a matrix, each element in that matrix is defined as the interaction between two basis states. So in the basis states, just to kind of clarify, there's a lot of different words you can use to talk about the same thing. What we mean is some electron configuration representing a specific occupation of orbitals. You can call it a basis state, you can call it a slated determinant, you can call it a configuration. All of them are referring to the same thing in this case. And if we look at the matrix element corresponding to two basis states, phi I and phi j, it's defined as this term, which is like the interaction between them. If we have the diagonal elements of the Hamiltonian, so HII, that's the expectation value of the Hamiltonian on that basis state. So that would be this expectation value phi I, H, phi I. And then we have two more cases. The one case is where the electron configurations represented by the two basis states differ in occupancy by more than 2 electrons. So if we had to visualize the orbitals, let me say that we compare the list of orbitals and which ones are occupied and not, and we find that the occupied lists differ by more than 2. So there's more than 2 electrons that are in different places between the two basis states. Then this matrix element is 0. There's no interaction between them. But if we have that difference is 2 or less, then that matrix element gives us the energy of the excitation. So if you have a certain basis state that is like one configuration of electrons, and you have another basis state which is exactly the same except for one electron is in a different position, you can generate that second basis state by applying a single excitation. You move an electron from one place to another place, and this matrix element gives you the energy contribution of that excitation. So we saw that the terms in the Hamiltonian are defined, or the elements in the Hamiltonian are defined in terms of the basis states. And if we change those basis states, we can change the basis that the Hamiltonian is represented in. So we have the condition that the basis states need to be orthonormal, so they need to be orthogonal to each other, and they need to be normalized. But if we satisfy that, we can then recompute those matrix elements using this expression in the different basis. And what we get is the Hamiltonian represented in now a different basis. And so it's slightly different. And sometimes you can pick out other information easier when you change the basis. So what quantum SCI does is it performs selective configuration interaction. So we try to make a wave function that isn't exponential in size, but does have all of the majority of the correlation that we're looking for. And we use a quantum computer to do the configuration search rather than using a classical computer. So the space of all configurations in the system is exponentially sized because we have an exponential number of ways to order the electrons and the orbitals. And because of the way that quantum computers work, we can actually search the space efficiently because we use just a linear number of qubits to do this. So there is some motivation for wanting to do this with a quantum computer, and it can effectively help us to speed up that search for the configurations that we're using in our wave function. So we're going to use a quantum computer to identify the configurations in our wave function. To kind of get back to the trainability issue that we were talking about, when VQE tries to train the parameters in the quantum circuit, because we don't change the circuit, what we're really doing is we're solving for these coefficients in the wave function. If we were to change the parameters, so not just the parameters, if we were to change the structure of the circuit, we would be changing these Slater determinants or the configurations that are in the wave function. But we keep the structure the same, and what we do is we change the parameters. So we're trying to quantitatively set these coefficients. And because of the noise on the device affecting the energy estimation, our ability to train is essentially our inability to train is can be described as our inability to correctly set these coefficients in the wave function. But what we do when we use the SCI algorithm is we use a classical eigensolver to exactly set these coefficients. So rather than trying to do this on a quantum device, we're going to use a classical device to do it. But the issue is the Hamiltonian is too big. So the Hamiltonian dimensions scale exponentially with the number of electrons. So we need to somehow reduce the Hamiltonian so that it's small enough to diagonalize. And you do that using like with the SCI, we know that we can do that reduction, but you have to have the important basis states. So what we use the quantum computer for instead is to sample those basis states that we need. If we consider our wave function on the quantum device, we have the CIs. And what we say is that for quantum SCI, what we're going to do is instead of trying to target the true values, so if we're looking at a ground state, instead of trying to get the exact amplitudes that will give us the ground state, and we do that by training the quantum device, we will try to target approximate values of the coefficients that are simply sufficient to allow us to sample the correct configurations of the device. So we do this change from needing the exact coefficients to needing some approximate qualitative coefficients, and that allows us to get around some of the training issues that VQE has because we're relaxing the constraints on the accuracy. So in order to get those configurations that we need for our wave function, we need to perform sampling on the quantum device. So we still use an ansatz to prepare the state on the quantum computer with that it can be parameterized. And what we do at the end is we sample each qubit in the computational basis, and it gives us this output. So these bit string states are like the representation, the computational representation of a configuration, or we call it configuration or Slater determinant or basis state. This is what I mean when I talk about those. I mean a series of zeros and ones. Each index represents a specific orbital. So this would be orbital 1, orbital 2, orbital 3, and 4, and so on. And the value at that index represents its occupation. So if it's 0, it means that that orbital is unoccupied. And if it's 1, it means that the orbital is occupied by an electron. And when we execute our quantum circuit on the device and then sample or measure each qubit, we get a 0 or a 1 when we collapse the states of the qubits, and that gives us these configurations. So we have this set of configurations, and knowing from SCI, those configurations make up these parts of the wave function, the configurations in the wave function. So the quantum computer gives us those, and now in order to reduce the size of the Hamiltonian so that we can actually perform the diagonalization, we need to use those basis states to calculate the matrix elements, because we can do a projection into a smaller space. But there's a constraint on this. We can only use configurations that are valid for the system that we're considering. So if we have a chemical system, it has a defined number of electrons, it has a defined number of orbitals, it has some other properties like total spin. We will only use configurations that satisfy those requirements. So for example, we'll only use configurations that are electron preserving, so they have the correct number of ones in them. And we will only use basis states that are spin preserving, so they have the correct like allocation of ones. So to see how this would look when you're doing this filtering, we have the full set of configurations that we've sampled, and now we go through that set and we remove all of the ones that are invalid. The reason that they're invalid is because of noise. So we can have bit flips at the end when we're reading out the measurement, and they can take a valid state and turn it into an invalid state. We don't necessarily know what that state was before it was invalid. Going back is another area of study of trying to kind of recover what the correct one was. But if you're just doing the filtering, you're not going to worry about what they were before they were wrong. We're just going to say, okay, it's incorrect, you need to take it out. So if we have the electron preserving consideration, what we'll do is we'll take a basis state, and in this example, I'm going to assume that basis state with three electrons is valid. So it's a system with 3 electrons. We will remove all basis states that don't have the correct number of ones. In this case, that's 3. So this one is correct because it has 3 ones in it. This one is incorrect, it's got 2. If it had 4 ones, it's also incorrect. And then in that case, it has too many electrons. So we can apply that filter. And then in order to apply the spin preserving filter, we need to take a look at the indices of the ones. So for each orbital, a spatial orbital, there's 2 spin orbitals for that. There's an alpha spin and a beta spin, and they kind of represent the 2 spin components because of the electron nature. And when we consider our basis states, we're going to make the assumption that all of the even indices represent alpha orbitals and all of the odd indices represent beta orbitals. So in a system that has one alpha electron and 1 beta electron, which has a total spin of 0, we need to make sure that the number of alphas matches the number of betas. So in this case, this state is wrong because we have a 1 in an even index, so that's an alpha electron, and then we have another 1 in another even index, which is another alpha electron. So we have 2 alpha electrons, no beta electrons, and our total spin is not 0. So we throw those states away. If we consider this one, we have 1 alpha electron and 1 beta electron, and then we know that this is a valid state because it is spin preserving. So the exact rules of what is the spin that we're looking for, that will come from the chemical system that we're considering. So if it has an unpaired electron, then the spin will be different. But in these cases, like what we're going to do for spin is we're going to check the indices of the ones. What we do for total electron check is we're going to check how many ones there are. So now that we've filtered out all of the basis states that we got that were invalid. We are left with a set of valid basis states, and we can project the Hamiltonian into the subspace now. So those configurations that we sampled, the number of them is not exponential because we didn't perform an exponential number of measurements on the quantum device. So we have some small set of them. And when we project our Hamiltonian into this basis, it reduces the dimension. And it reduces it enough that we can actually do that classical diagonalization. So we just simply compute the matrix elements using those states that we sampled that were valid. And then we get this small matrix, which we refer to as a subspace matrix. And we can actually now do the diagonalization because we don't have this exponential computational overhead. So that brings us to this step. Because there's a reduction in the dimension, we can exactly diagonalize the subspace Hamiltonian, and that gives us the exact amplitudes. So if I just skip back a couple slides to the wave function definition, in the VQE algorithm, we're using the quantum device to try to train to get these coefficients, and because of noise, it's not really possible to do this to a high level of accuracy. But with the quantum SCI algorithm, we use the exact diagonalization to set these. So we get a more accurate answer than normal VQE. So when we perform SCI with a quantum device, we get more accurate solutions than using the VQE algorithm because we exactly set the amplitudes of the configurations. And the issue with SCI is, of course, trying to figure out which configurations are the ones that are important. And using the quantum computer to simulate the system can actually improve the efficiency of that configuration search compared to just doing it normally on a normal device, a classical device. So that brings us to the end of this lecture. So we covered the two issues with some quantum computing algorithms, which are the trainability and the circuit depth. And we showed that for the circuit depth, you can use dynamic construction to try to make powerful ansatz that are still shallow enough to use. And we showed that with the trainability of VQE, we can kind of avoid this by relaxing the constraints on the training of the coefficients in the wave function. So those are some of the most advanced methods at the moment. There's obviously a lot that could have been covered here. I just chose those two specifically. But those are some of the methods that we use for the training of the ground states on the device. So if we just now consider the mini school as a whole, we have just a quick overview to kind of tie everything together. So just to begin with, when we were considering the problem of electronic structure, we know that we can try to use computer simulation to do this chemical modeling in a way that reduces costs or experimental costs, because we're not doing now experiments in the laboratory, which are time consuming and expensive. We can try to do a lot of simulation on the device to output a few candidates that people can then validate in a lab. And the reason we do this is because we want to try to study the properties of chemical systems on the computer with the simulation. And that's really relevant for industrial applications because it helps us see what are certain properties that we might be interested in. And you can use classical computers to do this. It's been done for a long time. The methods are very well studied. And the issue is that the issue is in the nature of the systems that we're studying. So these chemical systems obey quantum laws, and we have an exponential scaling in the number of electrons. And when you try to apply these classical methods to this problem, we have an exponential scaling in the memory because we're having to try to consider all these different possible configurations. And that's the biggest problem. It's just a limitation of these methods to small systems. And when we try to increase the scale of the chemical systems that we're looking at, we have to start introducing more and more approximations to reduce the memory cost. But an alternative of this is to actually use quantum computers to do the simulation. So the chemical systems behave quantumly, but so do the quantum devices. So we can try to avoid that exponential increase in the memory requirement for simulating the systems. And this can, in theory, provide an exponential speed up for this chemical simulation. The problem is the state of the current devices. So with fault-tolerant quantum computing, which has error correction, we can realize that exponential speed up. But at the moment, we still have a long way to go before we can get to the fault-tolerant regime. We just currently have NISC devices, which are noisy and there's some caveats with them, but there's improvement all the time. There's improvement on the hardware side. So there's research into a bunch of different technologies. No one knows exactly which quantum computer like hardware is going to be the one that scales and provides the solution we're looking for. And maybe there won't even be just one, there could be multiple. But in that field, there's always advancements every year. If you look at the graphs released by IBM and some other companies, you see that they're making a lot of improvements in the error rates of their devices and in the number of qubits in their devices. And on the software side as well, there's a lot of improvement in the algorithms that are being used to solve the electronic structure problem. So for the moment, it looks like a really good in between is the collaboration between classical software or classical hardware and quantum hardware. And as time goes on and the quantum methods will increase, it'll be able to take on a lot more of the workload until eventually we can just use quantum computers to do these simulations. And it's exciting because if we are able to do that, then it'll have a really big impact on the world around us, because we'll be able to do drug discovery, discover new medicines to treat certain illnesses. We'll be able to design new materials for things like batteries and a lot of different really interesting applications. So it's an exciting field, and I'm really grateful that I had the opportunity to share this with all of you over the past 4 weeks. So that kind of concludes the school, and I'm just really grateful and would like to thank all of you for your participation.
Okay, thank you very much, Shane, for that lecture. And yeah, thank you for also volunteering to share this really interesting information regarding quantum, using quantum computers to simulate quantum chemistry. So I don't see any questions in the Q&A at the moment, but if anybody has any comments or questions, please feel free to either type your question into the Q&A now, or please raise your hand and I can give you an opportunity to ask your question in person. So maybe I can just say, so we had a comment from Christopher Cohen, who says, "Thank you so much. These lectures were very interesting and informative."
No, it was a pleasure.
Okay, if there's no questions, or if anybody doesn't want to raise their hand, then maybe if people have questions, or they think of questions later, they can perhaps email you.
Yeah.
Is your email available?
Yes, I can provide my my student email in the chat here.
Okay, great. Yeah, so if anybody, if there's no questions, then let me again say thank you, Shane, for sharing this with us. And yeah, if people have questions, then feel free to contact Shane. So thank you very much, everybody. And yeah, thanks. Have a good afternoon.
Thanks, everyone. Bye.